afternoon, evening, wherever you are. Before we begin, I wanted to mention that Canada's only Synchrotron research facility located in Saskatoon is situated on Treaty 6 land and the homeland of the Métis. As educators, we respect Indigenous ways of knowing and oral traditions. We dedicate ourselves to moving forward in the spirit of partnership, reconciliation, and collaboration. My name is Anna Maria Beckler, and I am the Education Coordinator. Myself and the Education team are here to moderate this seminar to ensure your questions and comments are heard. As we get started, I'd like to remind you of a few things. We are recording this, so those that are unable to join us at this time can still engage later or use this with their students. If you prefer to keep your camera off for this reason, feel free to use the chat function to ask questions or comment. Please keep your microphone on mute when you are not trying to talk to us so that we can keep a background noise to a minimum. And for this seminar, please keep your questions to the end. You are welcome to write the question in the chat function, but it will not be read or answered till the end of the talk. So I am excited to introduce to you Dr. Adam Gillespie. He is a faculty member at the University of Guelph's School of Environment. He is a soil chemist with a research focus on soil organic matter, characterization, mapping, and modeling. He has a strong interest in using innovative research and instrumentation to link land management with soil health and sustainable land use, such as the Canadian light source. Today, he'll talk to us about soils and synchrotron techniques, along with a couple of case studies. Thank you, Adam.
What a tremendous introduction. I had no idea that any of those things were happening. Thank you so much. A couple other things I just will throw in there. So I live in Guelph now. Guelph, oddly enough, is my hometown, and so it's sort of strange that I got to come back here. I lived for 12 years in Saskatoon. I did both of my graduate degrees there, and I worked at the light source for a little bit. And so to all you educators out there, I've done a few projects with students on the beamline, and might have even been on the first one, although maybe the first or second, doesn't matter. So I'm really thrilled that you guys are doing this, that you have an interest in it. It's such a great program. Tracy's been doing I mean, it's just really grown into something that is quite notable. And so I'm thrilled to be a part of it. And I'm also thrilled to talk to you about soils and why it is that I'm excited about soils and synchrotrons and that sort of thing. I'm going to share my screen now. How does that look? Can people see my screen?
Yeah, now I see X-rays and soil science.
I hope so.
This dude named Adam.
Good. X-rays and soil science. So here is, I'm going to talk to you a little bit about X-rays and soil science and why it is that we get so excited about this kind of stuff. Actually, I should probably do just a wee bit of personal housekeeping in the sense that probably until about 1:30 is when we have this particular time booked. I can probably fill nattering away here for about an hour. Is that too long? Tracy?
I think that would probably be okay.
All right then. So let's, and I think maybe the right way to do this, I'll go through and we'll talk. I'll talk about what I have to say here, and then we'll have a big questions and discussions at the end. Okay. Well, here we go. I always like to point out that as a society, we find that soils are extremely important. And this is one of my favorite posters. This was actually put out by the British to entice people to have their gardens during times of scarcity. And so they taught a lot of people how to properly grow crops and to feed themselves. But we also see soils being a big part of big art. I mean, this is, whoops, sorry, that's a Van Gogh, and it's called Peasants Digging. I think we, more and more as we move on, we realize how important soils are to our very being and also to our, our culture and to how we feel about supporting ourselves. Soils are really important for feeding us. And one of the things I also like to point out is soils react to how they are managed. And this particular picture here, these are the same soil, same place, just in one spot it's been under grass, and in the other spot it's been under continuous cropping for many years. And you can see immediately a difference in how it looks. The soils that have been managed heavily tend to have compaction problems and different blocky structures. And you can imagine how difficult it is for plants to grow there and how difficult it is for water to move there. If you blow that up to a larger scale, for those of you who live in Western Canada, this is what this is the area that drains into Lake Winnipeg, and you live there. If you live in Saskatoon, the woman who lives in southeastern Saskatchewan, there you're draining into the Lake Winnipeg watershed, and they've had a lot of problems with algae because of too much fertility. So these management decisions that can be made all across this agricultural region will have an impact quite far away. And this last one that I like to show, it's a very pretty soil because of the colors. But actually, if you look up at the top of that picture, it's just quite an infertile soil. It's quite white. And nonetheless, that is a plow layer. So whoever is farming this area has actually, that's the only soil they have. So they're trying to grow crops there. So even though it's a pretty soil, it doesn't support agriculture very well, despite people trying to use it as such. One final picture that I like to put out now that I live in Ontario, this was an algae bloom in Lake Erie in the Great Lakes. That was so bad in 2014 that the city of Toledo in Ohio had to shut down their water supply. People were being poisoned by some of the toxins that the algae were producing. And so we think that we've got a lot of these environmental quality problems managed, but we really do not. So that's another thing that we think a lot about, environmental quality and the links between soils and agriculture. Okay, so now that I've sort of set the stage with the doom and gloom, I'm going to talk a little bit about, well, this is the outline of what I wanted to talk about today. Start off about, why is synchrotron research good for soils? But first I'll take a little bit of a sidestep and just talk a little bit about soils in general and what we're thinking about when we think about soil science and how soils are developed. I'll talk a little bit about the synchrotron. I'm sure you've talked about it a bunch, but it's always nice to have the same message come at you a couple of different ways. And then I'm going to jump into some case studies. So I've got some studies on 3 different elements, and then I'm going to talk a little bit about how we can use a synchrotron to study soil structures. All right, so here we go. This is, of course, obviously, as a soil chemist, my favorite cartoon of all time. This is from the far side. Early chemists described the first dirt molecule. And I always like to say that this is clear evidence that humanity has been studying soils for a very long time, soil chemistry in particular. But really, when we think about soils, we have to remember that they are really very complicated mixtures. Soils contain different minerals. Soils contain organic matter in different concentrations. They have organic matter of different types as well. Soils are alive, so they have microorganisms living in there, as well as worms and bugs and all kinds of other little critters. Soils contain water, and soils are always either drying or wetting up. So they're always in a constant change of water content. And then if there's not water, then there must be some kind of gas there. And so it can be like you would have in the atmosphere, but since there's respiration down there, you often have different mixtures of what we would normally consider air. Soils are extremely variable. I mean, we can look at that picture that you've already seen once. You just go down a couple of feet and you can already see that there's tremendous spatial variability, but even across the landscape, we all know soils at the top of a hill are quite different than soils at the bottom of a hill, just because of how water moves. And despite the importance of soils, a lot of what is in soils, we still don't understand. A lot of these components don't have easy structures to figure out, and so they're poorly characterized. And this is what we still are trying to work on as soil scientists. So how about a little bit of soil science introductions? When you dig a soil pit, you will see that there are layers. And this is a soil pit that I dug, so I don't even have to cite anybody's picture. I just cite myself. And what you see is these different layers. We, as soil scientists, will break them out into horizons. We usually call them A's and B's and C's. The A's are right near the surface. The B's are in the middle, and the C's are at the bottom. And often the A horizon, in this case, you can see is brown or dark, and that's usually because it's had a lot of organic matter added to it because of the plants that are growing there. But you can see there's a really sharp bottom line there where that A horizon turns into the AE. And that's because of agriculture. That's the plow layer line. And so in natural soils, that line can be distinct, but not quite that distinct. So that's quite an impressive change that agriculture has brought to what soils look like. Now, the AE horizon means that it's bleached, and soils, all soils are going to have things that move down with water. Things that move down include iron, it can include clay, because this happens over thousands of years. And so what's left behind is that sort of bleached layer. And what that means is that anything that was brought down is going to be deposited somewhere, and they are always deposited in those B layers. So the B in this particular instance has got a little bit of iron, a little bit of clay, but you can also see that it's got red spots on there. And those red spots are rust. Anytime you have wet places that wet and dry, you're going to start to get rust spots. And what this tells you is that this particular soil is sometimes waterlogged, depending on the time of year. And then at the bottom is what we call the C horizon, and that would have been the stuff that the soil started out as before all soil forming processes took place. So we call it parent material occasionally. And in this particular soil, this stuff is from limestone, which means it has a lot of calcium carbonate in it. And that's, if you were to take a little bottle of vinegar and spray it down there, it would bubble. It wouldn't bubble at the surface, but it would bubble down there. And so that material, you can consider it to be what the soil would have started out as before plants were growing there. Take a little moment here to talk about these rust spots. We call them mottles, and we find it really, I mean, I find them interesting because they're pretty, but I also find them interesting because it tells you a lot about how that soil developed over time. Normally, we think of soils as being static, I guess, and we've got to remember that there's always going to be water coming up and water going down. And if you start to see these rust spots, it means that sometimes of the year, those soils are going to be wet and in reducing conditions, for those of you who are chemists, and then other times of the year, they're going to be dry and they'll be oxidizing. And that's why you get a combination of different kinds of iron. You got the red iron because it's oxidized and rusty, and you got the gray iron, which is reduced. I find that pretty interesting. All right, let's have some examples of what a soil profile might look like. So this is a soil that was developed on clay, and the clay did not let any of that water leave, so very poor drainage, and what you end up with is a big layer of peat moss on top because it does not decompose properly. As you go down into the profile, you can see that those gray layers there, those are the we call them sometimes blue clays because they never dry out completely. And so you always end up with this sort of gray clay, gray iron, I guess. And then at the bottom of the pit, you start to see a little bit of that rust creeping in there. So that would be something that we would call a very poorly drained soil in a swampy area. I'm thinking you probably have a bunch of them in northern Saskatchewan. Let's contrast that with the forest soil. You can see this particular one, you don't see really very much of that gray stuff at all. At the bottom, it's kind of powdery and yellow. And in the middle, it's sort of brownish. And at the top, you have a lot of organic matter that comes in from any trees, leaves and twigs and that kind of stuff that dies and gets incorporated into that top layer. Really high organic matter soil, but very different in terms of how it behaves because a lot of that water drains out. And then this last one here, this is a soil, shall we say, has been abused in the agricultural practice. And I picked this one on purpose. They're not all this horrible looking, but what you have here is a soil that's lost a lot of organic matter. But furthermore, this soil has been worked so much with farming equipment that actually the material that normally would be buried has been brought to the surface. So remember, I was talking about these soils being limestone based. So the limestone now has been mixed in all the way to the surface of this particular soil, which is a big problem because it actually reduces the fertility of that particular area. Okay. Now, soil texture is another thing we always talk about. And soil texture, some people call it particle size analysis. And really, it's just the mixture of sand and silt and clay particles. And you see in the bottom left, I have a diagram there. You got to put kind of the relative sizes of what sand and silt and clay would be. And I should point out, like, I think most people know what sand and clay are. But in our world, we actually assign numbers to it. And those numbers kind of, when we put them all together, then we can have a bit of a shorthand when we talk to other soils people about what a particular soil texture ought to be. And so sand is anywhere from 2 millimeters down to 50 microns. And then the clays are anything that are 2 microns and less. So it's really, really small. I got a couple of pictures there on the right. A nice little close-up. This is what a sand might look like. If you're trying to squeeze it, it's never going to make a ball. It's just going to fall apart in your hands. But if you find a nice clay, you can usually make a ribbon. And of course, that's the reason people use clay to make pottery. It's also one of the things that we do when we're out in a field, when we want to figure out how much clay do we think actually is in a field. We try and see how big of a ribbon we can make. And so I'll share with you this picture. That's me, right? And what am I holding there? I'm holding, we call that the worm. It's a very heavy clay. On this particular site, we got about a foot long of ribbon. I felt pretty proud of myself that day, which gives you an idea of how bored I must have been. But anyway, that was a wonderful, an example of a very heavy clay soil. Now, I mentioned that soils are variable. Okay, so this is a soil map for the city of Ottawa. And the city of Ottawa is right in the middle there. And I guess I say the city of Ottawa. It's all the farmland around the city of Ottawa in Ontario. And it shows in this particular map the different textures that you would find. I guess what I'm pointing out here is that you can have quite drastically different soil types and soil textures in a small area. And I'll give you an idea here. This here, sorry, I should say anything that's green means that it's more of a clay. Anything that's red is more of a sand, all right? Orange and red is more of a sand, and a yellow is more of a fine sand. So what do we have here? This is an ancient shallow sea. People, and I guess I can say this now, people in the area who live there, they don't laugh. They call it Ottawa's Saskatchewan because that particular area is really flat. And I always kind of smirk at them and say, yeah, you keep telling yourself that. But it is. It's very flat and a big clay plain, very similar to what you would find around, well, it's a flat clay plain. I'll just leave it at that. But if you go over here, this area is an ancient delta. So at one point, the Ottawa River was there, and it dumped a bunch of sand in that particular area. And then over here, right next to the ancient shallow sea, you have an ancient beach. And so that's very, very sandy. And so I guess the point of all this is that you can have very, very different soil textures, very different soil types in a small area, even at the county scale like this. Or I mean, look at this beautiful picture. This is a picture from Saskatchewan. You can have a different soil at the top of that little hill compared to the bottom. You can see the organic matter is a lot deeper at the bottom than it is at the top. And in fact, if you look at the bottom of that hill, just underneath those birches on the right-hand side, you can see that they're starting to get a bit of that bleaching layer. So there's so much different, so there's such a different water movement between the top and the bottom of that little hill that you see that big difference in soil formation. And so I really like that picture a lot. And this last one to talk about soils across Canada. I mean, even across a country. I mean, it's a big country, but you can see we got all these different kinds of big soil regions. The soils of the prairies, we typically look at them as being grasslands. The soils down here in Ontario are broadleaf forest soils. If you go into Quebec, those are more boreal forest soils. And so we have these big, large-scale differences all the way down to very fine differences depending on where you are on a hill. And so that's sort of the excitement of why I like soil science. That was not so bad, eh? That's my intro to soils. Now, the synchrotron, why would we ever want to use a $200 million research tool to look at dirt? Well, good question. Soil science is involved in so many different areas of social needs, and we've got a lot of societal problems that tie into it. We've got contaminated soils. We've got animal agriculture and disposing of manure. We have mining and smelting in many areas of Canada and around the world. We've got hazardous waste storage. And then we have questions about sustainable agriculture, which is the one that I tend to get into more these days. How are we going to continue to feed ourselves with the land that we have? Now, if you look at the history of how soils and agriculture chemists and scientists have worked, typically what we do is we steal techniques after they've been developed, normally for medicine or physics or material science or biochemistry, any of these sorts of things. So NMR, which is sort of the scientific word for MRI, if you go to the hospital, any of these separation sciences like chromatography, mass spectrometry, X-ray diffraction, all these different techniques are things that were developed usually for, again, medicine or physics, but then we use them now to characterize soils. And so synchrotron is no different. This is a machine that we can use to characterize materials, and soil is a material, right? So let's give it a whirl. Now, synchrotron, as you are now in your third day, you now know this is a facility that is built to generate light. And we use this predominantly to investigate materials. That's sort of usually the way that I talk about a synchrotron to people. It's a sort of a materials analysis facility. And today, what I'm going to talk about is sort of how we can use it to look at chemistry, and how the benefit of a synchrotron allows us to be specific to certain elements, and then how we can use a synchrotron to look at structures, and in particular what soil pores would look like. Now, one of the things that would really be great for soils research would be to look at the samples in as close to a natural state as possible. So can we look at them with water and air? Can we look at them as a mixture? Can we look at as many elements as possible? And we try, and even a synchrotron isn't able to satisfy all of those requirements, but we can usually get close in some areas. And so what the synchrotron does allow us to do is to do some of these analyses quite quickly on mixtures, on these sort of natural states. And then we can also use synchrotrons to start feeding more modern artificial intelligence algorithms to tell us more about soils. We can use that as feedstock data, which is quite interesting and seems to be interesting to the younger people. I love X-rays, and that's what I'm going to be talking about now. Why do I love X-rays? Well, we know X-rays from the hospital. You can think of an X-ray at the hospital as being like an X-ray light bulb. and it's able to penetrate some of your features to tell you whether you have a broken bone or not. But in terms of synchrotron use, we think of X-rays as being just an extension of the light that we can see, of the rainbow. X-rays are the same kind of wavelengths, they're the same kind of phenomenon, and so you should be able to filter them and direct them and make them smaller point sizes as you would the light that you normally see. And so that's the way we do it. To study soil, we can think of X-rays as being able to study the chemistry. And today I'm going to be talking mostly about this X-ray absorption spectroscopy, which I think is what you're going to be doing on the IDEAS beamline if you use it. The studies I'm going to talk about today, one of them will be to talk about the nature of soil carbon. Another one will be to look at sulfur redox chemistry. I won't be talking about phosphorus chemistry, but I will be talking about the metal speciation in soils. And then for the structures, I'm going to talk a little bit about something called computed tomography, which is exactly the same computed tomography that you do at the hospital, and then something called X-ray diffraction. And both of these tell you what soils are made up of rather than what the chemistry is. Okay. So let's start with the whole chemistry story. What's amazing about X-rays is that they have about the same energy, the sort of same range of energy that it takes to promote an electron in an atom. So whereas, you know, the rainbow, like a color green, is what tells you that there's a leaf or a chlorophyll, X-rays are able to be tuned or be able to match the same energy that it takes to move electrons around in an atom. So say, for example, you've got your atom and they've got their different electron shells. Remember that from chemistry, you've got these different shells. What can happen is you can send in that X-ray and it'll pop that electron up to a higher state. And then if you just wait a moment, that electron can come right back down again and it'll release a photon out, sort of the same energy. And this is really interesting because maybe you guys have already talked about this, but every single atom, every single element on the periodic table does this at its own energy. So the energy required to bounce a silicon is different than for aluminum, is different from magnesium. And so what you can do then is you can start to pick and choose what element you want to look at. Furthermore, you can also use the same idea to look at all the elements at the same time. So you see, doesn't matter what, you can hit that sample with a really high energy X-ray, and then you can see how much of all the other elements are in there. So this is a very, very useful way to get a feel for what each element is doing inside a particular sample. This is really important for soils because soils have got all of these different elements in them. So like I just pointed out, once you get through, you've promoted that electron, if you're looking at a particular element, and I'll use as an example silicon, you would notice that once you cross that particular energy, like that specific energy that excites silicon, you will get a jump. You'll start to say, oh, look at that, I found silicon. That's the energy that excites it. But what's amazing is that if you focus in on that jumping area, you will start to notice that there is more structure in there. You'll start to see there's more peaks and more valleys. And that is one of the beautiful things about X-ray absorption spectroscopy, is that all of those peaks and valleys are diagnostic for the kind of silicon or the kind of element that is there. So each of those peaks might represent something a little bit different, different kind of chemistry of that particular silicon. And this is what we use, and this is the kind of approach we use when we're studying soils to try and get an idea of what that chemistry looks like. Here's an example that we collected on the SGM beamline, and you can see we're going through all of these different element edges, and you can see there's wobbles after each edge, and those wobbles tell you what the chemistry is of those particular elements. So you can see oxygen and iron and magnesium. And so this turns out to be kind of a fingerprint of these different elements in a particular soil sample. So once again, this is very important. X-ray absorption spectroscopy is element specific. It means that you can pick what element you want to look at and sort of filter out all the other elements in a particular sample. The beamline can be adjusted to filter only the X-rays that would absorb that particular element of interest and let you get, collect data on that particular chemistry, even in a complicated mixture like soil. So it means that you can do this kind of work on a soil sample with almost no preparation. You can just grind it and go. So this is a really, really good part of what doing the synchrotron work is all about. Okay, I'm just going to jump over these two slides here because I want to start talking about some case studies here. Are we okay right now, Tracy, so far?
I think we're doing okay. Can I ask you a quick question?
No. I mean, yes,
Okay.
of course. Yeah, no, go. What?
The units of measurement in one of your pictures, I think it was one of the pits.
Yeah.
Is that decimeters?
Yeah. Yeah.
Okay.
Yep.
Just checking. Thank you.
No problem. All right. Carbon. I love carbon. Carbon is the thing that I enjoy doing the most. And this study talks about studying carbon in the subarctic. And this particular study, I mean, there it is. That's the title of the study and the paper where it was published. Why did we get excited about carbon in the Arctic? Well, this is a graph that tells you how much carbon is stored at different biomes, I guess, around the world. So, I think we tend to think of tropical forests as having a lot of carbon, any forest for that matter, having a lot of carbon. And in fact, the tropical forest on the left has probably more carbon in the vegetation than it does in the soil. But if you go to the right side, the permafrost region has by far the most carbon store of any biome. And that's because it's cold. This carbon is not able to decompose properly, so it builds up. We can see that here. In fact, I think it's more than all the other biomes combined. We're thinking more and more about this carbon as areas in the north are warming, and that carbon might start decomposing, which would be a real drag because it would just feed into the carbon dioxide pool that is forcing global warming in the first place. So this is why we're interested in that particular kind of carbon. This particular study took place in Inuvik, and there's a map right up there, the Fraser River Delta in the Northwest Territories. And this is a picture of the site. So we're just below the tree line. And you can see these trees, they call them the drunken trees. And my understanding is that the drunken trees are moving very slowly because the earth is permafrost, and as the ice moves, the trees will also change their direction. And so this is what happens. Oh, I'll go back to this one. In the foreground here, you can see some lichens. And what happens in these areas, something called cryoturbation. Cryo meaning cold and turbation meaning mixing. And you end up with these earth hummocks across the landscape. And these earth hummocks are formed when ice starts to mix one 1 meter cubed, I would say, ball of soil. And you end up with sort of a mixture of the peaty material at the top, this mineral soil in the middle, and then as you go down here at the ice surface, you can see that there's more peaty material. And that's stuff that's actually been dragged under because the mineral part of the soil is very slowly spinning because of the ice. And so we call these cryoturbated earth hummocks. Here's some labels as to what kind of soil we would see. We've got organic materials at the top. We've got buried organic materials and frozen organic materials at the bottom. And in the middle of this dumpling, I guess if you want to call it that, we have these different kinds of mineral soil. So this is what we have up in the north. And this is quite widespread as far as soil structures are concerned in that particular area and across the whole polar region. And so since we are thinking a lot about decomposition and whether this carbon is going to decompose and release carbon dioxide, we wanted to know how bioavailable is this carbon, and does the chemistry of the carbon have anything to do with that bioavailability? So the first thing we did was we did some basic soil analysis here. And we did something else called a mineralization study. Mineralization, big word, really all we're doing is we're measuring how fast the microbes can decompose this particular soil. It's easy to do. All you need to do is put them in a mason jar and measure the amount of carbon dioxide that comes off over time. Do it for 3 months, something like that. And what I have in this figure is the different horizons from top to bottom. So the organic horizons, the OH horizon is the one that is buried but high in organic matter. The B is the mineral soil in the middle, and then the C is the one that's actually under the ice. We actually drilled into the ice to go get that particular one. And I should say that the first column here, TOC, is total organic carbon. They have quite high amounts in the organics, which you would expect because they're mostly peat, 35, 41, and 16%. That's a lot. But the B horizon is kind of 2%, which is what you would expect in an agricultural soil. And the stuff that's buried is actually quite low. Now, if you go over here to this column, what we did here was over 3 months, we measured how much carbon dioxide came off as a percent of that organic matter. And what we found was this fresh material right at the surface released almost 10%. Almost 10% of that carbon was decomposed, I guess, or respired within 3 months. But once you started to get into those buried soils, it was quite a lot lower, only between 1 and 2%. But the one thing we didn't expect was the material that had been frozen, the material that was underground and been frozen for a long time. It was actually more susceptible to decomposition than the stuff that was just above it. And you can see it was 2.6% of that stuff came off. So that was a little interesting. We were wondering why it was this material that was frozen was easier to decompose. So this is where the synchrotron work came in. We started to look at the carbon chemistry. And so here's an image of what a carbon spectrum might looks like for one of these soils. And what I'm going to do here is I'm going to show you how we try and look at this kind of data. Now, one of the ways I like to think about carbon chemistry is this. If you are at the store and you are going to buy a can of soup, maybe you're interested in the nutrition label, and you look at the nutrition label and you see that there are carbohydrates and there are proteins and there are lipids in that soup. And you are concerned, maybe you are on a low carb diet or whatnot, and that is what is going to make your decision. But the reason those things are broken out is those are different kinds of carbon. Carbohydrates are a different kind of carbon, and I can actually show it to you here. It's this peak. That's a carbohydrate type of carbon. A lipid carbon might be found more in this area of a spectrum, and then what was the other one? The protein ones might be found over here. The point being is that carbon is not all equal. There's different kinds of carbon in the environment, and we like to know that we know they have different functions because we see it on our nutrition label. It's the same thing when you're looking at microbes. They're thinking about different carbon sources having different kinds of energy and different kinds of metabolic importance. And so with this technique, we can look at aromatic carbons, we can look at these ketones and phenols, all these different kinds of carbon in a particular sample. Now, what happened when we started looking at the spectra for these Arctic soils was a pattern emerged where we had these ketones and these phenol type compounds. What we found was that when you were at the surface of the soil, I guess, the stuff that was fresh had a lot more phenols than the ketones. But as you started to go down through that earth hummock, you started to see a change. You started to actually see it becomes reversed. You lose some of those phenols, but you keep the ketones. And it goes back to the phenols again when you're in the buried material. And why this is really interesting is that actually ketones are degradation products of phenols. And what we think is going on here is that you have fresh material that you can identify because it has a lot of the original material, original phenols, and then the degradation products become enriched as the stuff gets older. What we still weren't able to, well, I guess what was interesting is that the material that was buried and frozen looked to be somewhat preserved in the sense that it still had a lot of the material that the microbes would find tasty and delicious. And I guess all this material still, it fits the pattern that you have at the soil surface. You've got material that is easy to decompose, gets harder to decompose as you go down, but then easier again once you get into the frozen stuff. So we were able to show that the chemistry did have something to do with how that material decomposed. So just to sum a bit of that up, the surface organic material was highly vulnerable to decomposition. The buried organic layer was slower to decompose. And we saw that there was this ketone marker as a microbial product of decomposition. But for some reason, this permafrost has a labile pool of phenolics, which might be because it's been preserved there from the freezing. And so what we find interesting and important about this study is that if the ice level, the permafrost table, that's the word I want to use. If the permafrost table falls, then you're going to expose a whole new pool of potentially decomposable carbon to be decomposed. And so that is that's sort of one of the flags that we put up with that particular study. Okay, so that's carbon. It's something that we call the soft X-ray region. There are soft X-rays, there's hard X-rays, which you may have already talked about, so I won't jump into that, but I enjoy always saying that there's also the region of tender X-rays. The tender X-rays are in between, and tender X-rays cover important soil nutrients of sulfur and phosphorus. I guess a lot of you who are well, if you're into farming, you would know this, but also gardening. NPK, nitrogen, phosphorus, potassium, and sulfur, those are the four big nutrients that we try and make sure we are doing a good job monitoring. And so this particular study looks at sulfur and sulfur fertilizer transformations. And let me talk to you a little bit about how the sulfur works. So sulfur is interesting. It's probably the third most limiting plant nutrient, certainly in Western Canada. In Ontario, we're starting to see sulfur deficiency as well. And don't laugh. The reason is because we're scrubbing coal-fired electric plants, and we're slowing down in general on production of sulfate that turns into acid rain. So on the one hand, we've done a great job with the acid rain problem, but guess what? We've got sulfur problems in our crops. So we're having to start thinking about sulfur fertility more and more. Plants take up sulfate, but there's more than one kind of sulfur compound out there, that's for sure. And so we're interested in studying how the microbial transformations of sulfur are important to the plant sulfur use. Sulfur, if it's not coming from fertilizer, can be released from organic matter. I think the easiest way to think about that is that there are sulfur-containing amino acids in your proteins. Cysteine and methionine are two of them. And a lot of times that's where the sulfur would come from for plant nutrition. So if you're thinking about using a fertilizer, there are many products available. and we wanted to know, how do they transform sulfur for plant use? So here are 4 common sulfur fertilizers. We've got ammonium sulfate, which people like because it also has nitrogen. You can use that for your nitrogen fertility. We've got gypsum, we've got liquid ammonium thiosulfate, and we also have elemental sulfur. So I'll use just a picture of a couple of them. I don't know if you have ever been down to the port of Vancouver. They have these massive sulfur piles just waiting to be shipped. If you've ever been up to northern Alberta to the oil sands, they've got massive sulfur blocks. So there's a lot of elemental sulfur out there that could be used for fertility if we needed it. And then there are these other products that are more manufactured as fertility amendments, and we wanted to check them out. So one of the reasons why we really like sulfur spectroscopy is what I'm showing you right here. Sulfur is a great example of how you can take a whole bunch of different reference materials and see the big peak shift depending on something quite straightforward, which is oxidation state of sulfur. Sulfur has an oxidation state anywhere from 0 to 6. And you can see elemental sulfur is down there at the bottom, along with the 2 amino acids, methionine and cysteine. And then it goes all the way up to sulfate, which is +6. And so those are the 2 that I kind of like to focus in on more, because those are the forms of sulfur that are in these fertilizers that you most often buy, the reduced and then the oxidized version. Now, when you look at these peaks, it's really nice to see them all kind of moving over as you increase the oxidation state like that. What happens when you measure the sulfur edge in a soil sample? Well, what you end up with is a combination of whatever happens to be in that sample. So this is a lot of fun. You see that there's multiple peaks, and we can trace those multiple peaks back to the one or the other kind of sulfur that I'll go back one slide here, that we measured in our standards just by lining those peaks up. That's what we did here. You can see we've got those different peaks. I've numbered them, and I only talk about a few of them here. The elemental sulfur, the organic sulfur, and then the sulfate is the big number 6 there. Now, this is what a particular soil looked like at week 1 after it had been fertilized with the elemental sulfur. So there was still a lot of sulfate left, but there was a lot of this elemental sulfur was in the soil there. But what happens after you go to week 8? Look at that peak number 1 again. I'll go back one slide. You see how the elemental sulfur is there and where the sulfate is on peak number 6. And look at how they're starting to change. The elemental sulfur is starting to go down, and the sulfate is going up. And what that's telling you is that you're starting to see a transfer of this elemental sulfur, which is really quite reduced, over to the sulfate, which is oxidized. And this is really a normal process in soils, but we're seeing it happen in real time with the spectroscopy here. And now what I'm going to do is I'm going to compare 2 of the fertilizers that we used and show you what that means in terms of sulfur availability for a plant. So on the left-hand side, this is when we use ammonium sulfate. Remember what I said, plants really like to take up sulfate. They don't like to take up other kinds of sulfur. And on the right-hand side, we've got something that was fertilized with the elemental sulfur. And what these lines are showing you, the red one is, I'll go back one slide here. Whoops, my mistake. The red line is the sulfate peak at number 6, and the black line will be this elemental sulfur peak here at 1. And what we see here is when you fertilize with ammonium sulfate, you've got a big, big, big flush of the sulfate material, and then it goes down because, well, plants are taking that material up and using it. On the other hand, you have a small amount of the reduced sulfate, but actually microbes will convert some sulfate into reduced materials, probably to use as amino acids or something like that. So that's kind of what you would expect. You put sulfate on, you have a big pile at the beginning, and then it gets used up. But look what happens when you use the elemental sulfur. You get a big peak of the reduced sulfur. You'd expect that because you just added it. But interestingly, the microbes very quickly convert it into sulfate before the plants have a chance to take them up. And so what you have here is you've got two different fertility approaches that give sulfur at different times. You can sort of think of it as timing your sulfur applications. Maybe you would have an early sulfate demand for plants that maybe are early risers, or maybe you did a winter planting, and then maybe you want to use this other kind of sulfur fertilizer for plants that you know are going to have a late demand. That way, you know you're getting the maximum amount of fertilizer use efficiency. So that's one of the sort of applied stories that we got out of looking at sulfur chemistry in soil. So to kind of sum those up, the different sulfur fertilizers will have a different, I guess, timing on what the plant available sulfur will be. The more reduced sulfur, or the stuff that you would get that's yellow, is normally you think of it as a slower release. And depending on the crop, you may want this. And also be aware, if you have too much sulfur and no plant growth, you could lose some of it to leaching. And that is another thing that reduces the cost effectiveness of that particular fertilizer choice. Okay. So far, so good. Now we're into the hard X-rays. The hard X-rays. Hard X-rays we typically think of as being what covers the heavy metals type of work in soils. There's other applications, but we think of mostly of it as being in terms of heavy metals and contamination. And so what I'll show you here is a study where we look at zinc contamination on soils that are surrounded by a smelter. So here's a picture of the smelter. I don't think it was any big mystery. It was all done in Flin Flon, Manitoba. I think the company was okay with people knowing where it was. They even wrote it in the academic journal. So this is a zinc mine with a tremendously long history. And as a consequence, they also have a lot of contamination issues in and around the city of Flin Flon and in and around that mine. The particular site that they were looking at seemed to be a bit peculiar because there were the landscape almost had two kinds of soils there. So they grouped them. They said, well, there's some soils here that are exposed on bedrock. They've got no vegetation and they're eroding quite horribly. But then there's another group, group 2. This group actually got sediment. It received things that came down from upslope, and they found that these areas were actually supporting vegetation, but it was a zinc tolerant grass that was invasive. And so while the soils were being stabilized by this grass, they weren't particularly happy that it was an invasive grass, and it was certainly not the original boreal forest that they would have seen at that landscape before the mine was there. So they started looking at the actual, just the zinc concentrations, and this is wet chemistry now. The group 1, which it's the upslope bedrock, you can see in the left side, that's total zinc, surprisingly, well, more or less lower than what is in the group 2, although if you got rid of that third site of group 2, you would say that they're all kind of the same in terms of the total zinc concentration. But what's interesting is that if you do a different test, an extractable test, and we often use extractable shaking tests to see, I guess, to mimic plant uptake. And the idea there is you would be getting a feel for how much zinc the plant would see. And we can see here that the group 1, which is the bedrock, really low, but the group 2, which is the sedimentary areas, which are supporting life, are really, really high with extractable zinc. And this kind of goes against what we would normally think of as being the story in a contaminated site. So that's where the synchrotron work started to come in. I put this whole pile of zinc standards in here just to confuse you and cause you some grief. The point being is that you can have many, many standards of a particular element that you can work with. And not all of the elements produce beautiful patterns like sulfur did. You end up with more these same sort of energy range, but slightly different patterns or slightly different fingerprints. But that's okay. You can start to match those fingerprints to your samples as you go through the data processing. Now, to sort of help you out here, I'm only going to really focus on 3 of them because they're really the 3 of them that we saw the most of in that study. One of them, this is my favorite, the franklinite, because it looks like it's got little horns on it. Then there's the zinc sorbed smectite. So really that just means your zinc stuck to a clay. And then this other mineral called sphalerite. And so the franklinite is a mineral, and then the other 2 are sort of a little bit more mobile, zinc sorbed, and sort of more simple structures chemically. Okay, so this is what the spectroscopy looks like of the soils that came from the field. And if you look at the group 1 in particular, you can see they've all got those, the real lumpy, the little horns shape to them, except for one, site 5 at death has a bit of a different shape to it, more like the sorbed zinc. But the predominant, I guess, structures there would be this franklinite. Whereas if you go to the group 2 soils, these are the ones that are supporting some life, you can see that they are mainly complexed with the one site there that has that franklinite on there. So, I mean, when I look at this, what I see are 2 sites with a slightly, well, with a different kind of zinc, not just different total amounts, but a different type of zinc chemistry going on there. Secondly, what they can do at a synchrotron is you can start to do images. You can start to look for zinc in a soil sample. And this is really powerful. You can see here in the group 1, the zinc is kind of spread out all around this particular area here. Same with the copper. It was also a copper mine there. And even in some cases, you can see it spreading out with the iron. So it was really kind of everywhere. I guess diffuse is the right word that we could use for that. Whereas the group 2, you can see it's hotspots. You know, those hotspots of zinc. So it's not diffuse. It almost looks like that zinc has been encapsulated in certain areas. So there's not just a difference in the type, but the difference in the distribution of that zinc. And so what I think is going on here is that you have, despite a high concentration of zinc, you may have the species of zinc playing a role in why some areas were grassed and some were not, and also a distribution of the zinc as to why some areas of that landscape were grassed and some were not. The one other thing I should point out, we should never forget that for something to grow, it needs soil. And so it could also be that at the top of that bedrock, there just wasn't enough soil substrate for those grasses to take hold anyway. And that having a soil substrate in the sedimentary areas were one of the reasons why it got going. Okay, so those are the studies I wanted to talk about in terms of the chemistry, and I think those are most relevant to what you would be doing on the ideas beamline. But I did want to share a little bit more and go back to the idea of using X-rays in ways that we would use them perhaps at a hospital for looking at soils, and that's why I put my 2 little, those aren't my hands, I stole that from the internet, obviously. But talk a little bit more about how you could use X-rays in this context to study soils. Computed tomography is really quite fascinating. You can make a 3D model of something using X-rays. It's the same approach that you would use if you were going to go get a normal X-ray, say on your broken leg or on your teeth. But instead of one picture, they take many pictures. They put the sample on a turntable and they spin it. And so you take picture after picture after picture on different angles. And then you can use all of those images, put them back together to build a 3D model of what you're looking at. Now, this is extreme math, but it is something that they do at the Canadian Light Source and, well, at the hospital. And so here's an example of a soil study that was done using computed tomography. We were looking at soil compaction. So driving tractors over soils. And what you can see here clearly is a difference in the non-compacted versus compacted soil in terms of what the pore space looks like, in terms of what the pore connectivity looks like. And this gives us a really good idea on what's happening inside a soil without us having to break apart a soil core. Very, very useful. And then there's another thing that we do with soils using X-rays, and that is identifying clays. You may say to yourself, what do you mean identifying clays? Well, you can use clay to make bricks, you can use clay to make porcelain, and you can also have clay that causes these shrink swell soils. These are all clay, but they're all very different kinds of clay. And it matters. It matters depending on, in case of agriculture, whether you've got this kind of very difficult to work soil, but it matters for industry. You need to use kaolin to make porcelain cups, and you probably aren't going to be doing that to make your bricks. And so that is where X-rays come in. They can be used to identify these different kinds of clays because the X-ray wavelengths are about the same size as the clay structures. And so what happens is you start to see those X-rays bouncing around in between those different clay structures, and it tells you what the distance is between them. And those clay distances are diagnostic. It actually lets you know what kind of clay is there. And just to give you an idea, if you are farming, the different kinds of clay can actually affect your soil fertility. These are 5 different kinds of clay. Illite, vermiculite, you've heard of all of these ones, or at least vermiculite, I know I have. But you can see their ability to retain nutrients is really wide ranging, anywhere from 20 to 1,500 sites per kilogram, or whatever that is you want to call it. A very wide range of how they're able to retain nutrients. The other thing that we can do with this X-ray diffraction is we can image those as well. Some people are interested not just in knowing what the elements are, which you see on the right-hand side, but knowing what kind of clay might be in a particular sample. This is really useful for metallurgical, mining exploration. It's very useful for all kinds of studies where they want to know how different minerals are assembled in a particular structure. Okay. I'm just going to quickly skip over that study and just finish off as a summary. So X-rays, they teach us a lot about soil chemistry, and they teach us a lot about soil structure. We can use X-rays to understand how elements are behaving in a particular soil. We can know a specific element speciation, and we can know its specific bonding structures. If we want to look at the physical layout, we can use X-rays for tomography to get a feel for what the pores and solids are looking like. And then we can also learn a lot about the crystal structures and mineral structures in clay. And these are all really important for soils and things that we use them for. And so I'm going to look at my, I got 10 whole minutes. That's a sandy soil in the background there. With a very distinct plow layer. A lot of fun there. But I'd be happy to take questions and talk about soils. And what I need to do now is get off my shared screen.